Welcome to This Explainer. Today we are taking a seriously enthusiastic descent right down the rabbit hole. We're leaving behind the safe, predictable, everyday world that we all know, and we are diving headfirst into the bizarre, invisible, and utterly mind-bending atomic realm. So get ready because the fundamental rules of reality, they are about to completely flip on their head. Okay, let's dive into this. We all intuitively feel that the universe is a pretty predictable place, right? But what if I told you that at the most fundamental level, the universe might literally be waiting for you to look at it before it actually commits to an answer? That is the ultimate mystery we're unpacking today. I mean, how can a single particle exist in two places at the exact same time? Well, to understand that, we first need to understand the rules that we're breaking. Section 1, the classical world and the rules of the everyday. Think about a reliable baseline of reality, the one crafted by scientific absolute legends like Isaac Newton, Galileo, and Maxwell. In our macroscopic, everyday world, the universe is basically a giant, predictable clockwork machine. If you know the exact forces acting on a baseball, you know exactly where it's going to land. Simple. But contrast that with the microscopic quantum realm, governed by pioneers like Niels Bohr. Down there, predictability is totally replaced by shocking probabilities. Instead of these nice, smooth, predictable paths, we get fuzzy uncertainty clouds and electrons making sudden, random jumps. Now, what's really interesting about this slide is how we can just map out this reality flip. Look at how literally everything changes when we shrink down to the size of an atom. In the classical column, energy is continuous. It's kind of like smoothly turning up a dimmer switch on your living room lights. But jump over to the quantum column, energy is quantized. It comes in discrete little packets, almost like stepping up the individual rungs on a ladder. And objects? They go from following definite, exact paths to existing merely in these hazy probability clouds. Section 2. Entering the quantum realm and the double-slit mystery. So how in the world did we actually discover this? Well, we can trace our transition down the rabbit hole all the way back to something called wave-particle duality. And this didn't just happen overnight. Back in 1801, Thomas Young punched two slits in a cart and actually proved that light behaves like a wave. Then, a whole century later, in 1905, Albert Einstein came along and proved light also arrives in tiny little packets, or particles, which we call photons. And then, in 1924, Louis de Broglie completely blew everyone's minds. He proposed that matter itself, literally the stuff making up you and me, has a wavelength. It was this stunning realization that the fundamental building blocks of the universe carry a dual nature. They act as both particles and waves. To brilliantly illustrate this, let's talk about the incredibly famous double-slit experiment. Okay, imagine throwing perfectly predictable tennis balls at a wall with two slits in it. You'd obviously get two neat piles of tennis balls on the other side, right? Now instead, imagine dropping a stone into a pool of water near two slits. The ripples spread out, they overlap, and they create a striped pattern on the back wall. So what actually happens in step 1 when we fire tiny matter particles like single electrons at those slits? Well, in step 2, if we don't observe them, they hit the screen and create striped patterns, just like the overlapping water waves. Wait, what? But it gets even crazier. In step 3, if we put a detector there to simply watch which slit the electron goes through, the stripes suddenly vanish. They completely collapse into two distinct stacks, exactly like the tennis balls. This brings us to a legendary quote from the great physicist Richard Feynman, who called this exact phenomenon the only mystery of quantum mechanics. Because think about what this actually means. This single experiment contains literally everything bizarre about the quantum world. The most terrifying and incredible idea here is that simply looking at something, the mere act of observation, actually changes its physical behavior. No way, right? But it's true. Section 3. Superposition and Schrödinger's cat. The observer effect in action. So to see how this weirdness scales up through one of the most famous thought experiments in all of history, we first have to grasp a fundamental concept, and that is superposition. Basically, a quantum particle exists in multiple possible states simultaneously. Think of a spinning coin. While it's spinning in the air, is it heads or tails? In the quantum world, it is literally both at the exact same time, just a fuzzy blur of possibilities. It only chooses heads or tails the very second it lands and you finally observe it. Which naturally leads us to Erwin Schrödinger's 1935 thought experiment. He asked us to imagine connecting that microscopic quantum weirdness directly to a macroscopic object. You place a cat in a completely sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the poison is released. If it doesn't decay, the cat is totally fine. But because that atom is in a quantum superposition of both decaying and not decaying until it's observed, does that mean the cat is simultaneously dead and alive until we open the box? Okay, here is a major reality check. Schrödinger's true intent was actually a critique. He was definitely not endorsing the idea of a literal zombie cat. He designed this entire scenario to highlight the absolute absurdity and chaos that would happen if quantum rules suddenly bled into our everyday large-scale reality. He was essentially asking the scientific community, guys, where do we actually draw the line? And honestly, physicists have been trying to answer that exact question ever since. There are many different interpretations of this measurement problem. The Copenhagen interpretation says observation itself triggers the collapse. The many worlds interpretation suggests the universe literally splits, one reality where the cat lives and one where it dies. Objective collapse says actually it happens automatically based on mass, without needing an observer at all. And relational quantum mechanics argues that reality itself is completely relative to whoever happens to be looking. So yeah, we still don't have one universally accepted answer.
Section 4. Quantum entanglement. Explained. The ultimate connection.
And this brilliantly illustrates our next point, because if you thought superposition was wild, just wait until we explore entanglement. This is where physical distance simply ceases to matter entirely. The idea was so controversial that Albert Einstein famously called it spooky action at a distance. He was deeply, deeply unsettled by it. Why? Because entanglement implies that two particles can communicate their states to each other instantaneously, regardless of how far apart they are across the universe. To Einstein, this seemingly violated his ultimate cosmic rule, that absolutely nothing can travel faster than the speed of light. To understand why it's so incredibly spooky, let's look at a quick comparison. On side one, we have the classic shoebox. If I put a left shoe in one box and a right shoe in another, and I mail one to Tokyo and one to London, well, opening the Tokyo box and finding the left shoe instantly tells me the London box has the right shoe. But that is not quantum entanglement. Those shoes always had a fixed identity from the start. Side 2 shows the quantum truth, the quantum socks. Imagine shipping two magic socks. They aren't red or blue, they are a fuzzy blur of both states. They genuinely do not have an identity yet. But the exact instant you look at the sock in Tokyo and it becomes red, the one in London instantly becomes blue. They literally make up their state the exact moment they are observed. Now, Einstein hoped that there were just hidden variables, secret pre-programmed instructions inside the particles that we just couldn't read yet, kind of like the shoes. But in 1964, a physicist named John Bell devised a mathematical theorem known as Bell's inequality, and years of subsequent experiments proved that quantum coins flipped on different axes behave in ways that are mathematically impossible if they had pre-decided answers. So Einstein was actually wrong about this one. The spooky, instantaneous connection across the universe is absolutely 100% real. Section 5. Real-world quantum technology. Zooming back out. So the crucial point is, this isn't just invisible math or a fun philosophical debate. These bizarre rules are powering our tangible future right now through some absolutely incredible real-world applications. We're actively building quantum computers that use qubits in superposition to process massive amounts of data simultaneously. We have quantum cryptography, creating totally unhackable networks because any attempt to observe the data instantly changes it. There's even quantum teleportation of data states and the design of advanced new materials. And keep in mind, without early quantum mechanics, we wouldn't even have MRI machines, fiber optics, or the smartphones sitting in our pockets today. It is a real game changer. But that begs the question, why don't we see this weirdness all around us? Well, the answer is decoherence. It's essentially the bridge between the two worlds. Think of reality kind of like a movie. Each individual quantum frame is discrete and totally unpredictable. But when you play trillions of those frames together all at once, the randomness just averages out. Your brain sees smooth, continuous motion. When you have trillions of atoms working together, classical physics reliably reappears. Which leaves us with one final, provocative question to ponder as we wrap up this explainer. If observation is truly what forces reality to pick a state, then the old philosophical questions aren't just for philosophers anymore. If a tree falls in the forest and no one is listening, does it actually make a sound? Or, as a deeply frustrated Albert Einstein once asked his friend, do you really believe the moon does not exist when you aren't looking at it? I will leave you to think about that one. Thanks for exploring the quantum world with me.